Good morning. How's everyone so far? We're into the end of our first week, first full week, sort of week and a half of the course. So let's kind of take a look of where we're at. How do I got this? Oops. Looks like that is not viewable, but we'll see. Okay. So we have taken a look at 1.2 and 1.3, caught up on 1.3, and then we looked at transformations as well on Monday. No, Tuesday. What day is it anyway, right? Then Thursday, what we've got scheduled is combinations of functions and compositions and inverse functions. So those are kind of two somewhat related. So we'll take a look at those. What I will do is over the weekend, I'm integrating this course with what I have, with the resources I already have. So I don't have those modules turned on. They're sort of there, but I want to update them, and I'll do that over the weekend so that those of you who may want to work ahead, you'll be able to do that. Again, I have online videos because I teach the same course as an online course, sort of the same course. It's not the STEM version. So what you guys get out of this one is primarily done in the recitation, but you get more practice with algebraic manipulations. The other course does some, but you guys do more. Okay, so we'll get those, but the concepts and stuff are all the same. In fact, we built the same. This course is built on by the same previous coordinator, Leslie Loy. She helped both of us separately put this together, and it was based off of a course that she put together in my math lab. So this one's actually closer to it. All we did is we took her my math lab class and we transitioned it over to an Alex platform. So we did make a few changes, but the content-wise is the order and everything else is pretty similar. Okay, so I will get all those resources posted. You're welcome to use those. Again, it is hopefully beneficial to be here in class, but as things happen and maybe you have something else, interviews, work, family related, if you aren't here, you won't be penalized for not being here. Only penalty is whether you learn the material or not. That will be reflected in the test and the material. So as long as you're staying on track and you're learning the content, you're going to be just fine. I do have I've sort of adjusted my office hours, so I'm breaking them into like half-hour segments before and after classes. So if you need me after class, just let me know. We'll find a place here. I'm available then. And then what I'll do is Fridays I don't have any classes, so I make myself available through Zoom. So if you need, Fridays are a good day to get Zoom tutoring. All you need to do is send me an email. We can set up a time. I have one set up for 2 o'clock tomorrow. And again, I do it sort of in half-hour time segments because a lot of times we don't need the whole half hour, but we'll work on it. If we need more time, we'll do it. But just contact me, let me know what you need, and we can get online and get you moving forward. Okay. And again, what we're looking for is we've got 2 more weeks. There is Labor Day in there, but that doesn't affect us because that's on a Monday. But we've got 2 full weeks of content, about 3 units, 3 segments each time, and then we've got our first exam coming up the week of 9/11. Looks like we'll do a review the Tuesday, and then we'll have the exam on Thursday. I have not seen the exams for this course yet. That's the other thing I'll work on this weekend to see if I can at least see some past ones, and I'll talk with the coordinator, see what those. But I'd like to have a feeling. A couple of you've asked me, are the reviews like the exam, and I just answered, I don't know. I assume they will be. That's how we've always done things. But since I haven't looked specifically, I'm not sure. The other thing I've been doing over the last couple of days, I can't remember when, but I've been turning on additional resources for the section. So Tamara has provided us with some notes and stuff, some additional notes. So those are there. Sometimes there's her PowerPoint that she came up with, so those are there. If you might take a look at them, they might provide some answers to something that's missing that I didn't have. And if you find something that was especially helpful, let me know, and then I can say, well, let me start incorporating that in the stuff that I do as well. There are some Desmos type things, so these will take you directly to a Desmos, and they're kind of nice because they have some sliders and you can kind of interact with them and see the concepts sort of come to life. And that as you do that slider, you see how the transition, you actually see it moving, so it makes, instead of just here it is and there it is, you see it move over to that place. So those are helpful. And again, she does it with 3 different functions. So we're going to go into 1.7, which I updated last night or this morning. I can't, no, it must have been last night. I couldn't get there. So I've got, again, this is the type of thing. It's module 5 in my course, but it's combinations and compositions of functions. So we've got a slide deck. We'll go from there. My section notes, again, we're even using the same notes. I add some things from the examples I do, so that's there. And then what you'll see is after today, by this evening, or maybe by tomorrow morning, we'll see what it is. I will post this lecture that we're recording right now. Hopefully, yeah, it's recording. Good. And then we'll do the same thing with 1.8 as we go through that. All right. Any questions or concerns that have come up? We're doing okay? All right. Okay, so combinations and compositions. So combinations are algebraically, we're taking 2 functions or more, but we'll do it with just 2 functions. We're either going to add them together, and that's kind of just like adding like terms, or we're going to subtract them, and that's distribute the negative through and then combine like terms. So those are things we've done probably quite a bit. Multiplying and then dividing. So those are the way we combine functions, right? Those are the 4 operations we have. When we get to composition is a different process. It's taking one function and putting it into the other function. So it's kind of like you get an input goes into one function, you get an output, that output becomes the input for the next function. So that's like maybe in a factory, if you're building cars, a lot of car factories, they don't actually make the steering wheel. That's made in a different place. So there's plastic or whatever makes those steering wheels. That goes in as an input. They make it into a steering wheel. That steering wheel now becomes an input into the car factory and goes there. So it's kind of like a 2-step process. So here's our composition of functions. Again, we're either taking 2 functions and adding them, we're subtracting them, we're multiplying, or we're dividing. And this is just some notation that we can write it either as sort of 2 functions being added together, and that x, the one thing that can happen is you see that because of the parentheses, it looks like we're going to take the 2 functions, add them, and then we're going to multiply them by x. But that's not what that's actually saying. It's saying that the x is a function notation, that's the input. Okay, so I always found that this side over here is a lot more helpful when I think about it. This has kind of always confused me, and I've always got to translate it over to here. So it tells me I've got f of x is a function, and I don't see that x as a multiplication. But over here, I'll see it many times. People will add the functions, and then they multiply by x, because that's what it looks like, right? But it's not. It's a sort of an inconsistency in the way they come up with this notation. But when we write it like this side over here, typically we have fewer problems. So we could use either notation, but what I said is if the problem has it set up with this f plus g of x notation, first thing I do is I'll translate it over to this notation over here. And again, all of these, because again, what I see is people keep multiplying by x if we use this side. Division and multiplication. One of the things we may face is the need to simplify a little bit. But we'll go through a few examples here, and then we'll talk about composition. So sum and difference of two functions. Again, it's all it is it's taking the two functions and combining like terms. So here's an example. And so we're going to take f and add it to g. Let me just, right? And so what does that look like? We'll do it here. Good. So we take the f function, we write it x squared plus 5x minus 8. We're going to add, and I'll put a parenthesis around it just to say that that's kind of like one package. And then the other package is 9 minus 10x. Now with addition, it's a little easier because if we distribute an addition sign, it doesn't change signs, right? So removing parentheses when we have addition, it really just becomes x squared plus 5, oh, I forgot the x, 5x minus 8 plus 9 minus 10x. And then we just combine like terms. Well, there's only one term that has x squared, so that's what that is. But then there's two terms that have x's, so I have 5x minus 10x. We combine that and we get negative 5x. And then I have a negative 8 and a positive 9. When we combine those, we get a plus 1. So that's combining with addition. Okay. Again, you don't have to put these parentheses at the beginning, but if you get in the habit, that will save you when you go to subtraction, because I'll see people won't put them with subtraction and they'll make the mistake of applying just the negative to the first term. Okay. So again, if we use the parentheses, it's x squared plus 5x minus 8. And I'll do this. We're going to subtract 9 minus 10x. And if you don't put the parentheses, you might stop it there. But when you put the parentheses, like you should, you see that what's going to happen to the negative 10x? That negative is going to distribute. It's going to become a plus 10x. And so this is where I see, again, it's just and I as a student, I made this error a lot as well. I still do. That's why I've learned put the parentheses, and then I won't mess up. So the first step is to distribute this, right? And so this is going to be, oops, I don't know where I guess I was looking ahead, and that's my problem, is if I go too fast, I start writing too fast and I leave things out. X squared plus 5x minus 8. So we see the first term doesn't, the first thing doesn't, nothing much happens to it. Minus 9 plus 10x. So, and then now it's just like the addition problem, combine like terms. Again, there's only one x squared, so that's all that's there. But this time when we combine the x terms, we have a plus 5x and a plus 10x, so now we're going to get plus 15x. And when we do the numbers, negative 8 minus 9 is going to give us negative 17. Okay, so that's, and again, in the homework you'll see these and just being asked. Multiplication of two functions. So here we have g of x and h of x, and so now we want to multiply the two functions together. And again, the key part is we're going to need parentheses around these. So g of x is the first one, 4x minus 6. H of x is the second one, x minus 5. And in a sense, this we're sort of done. This is the multiplication. We haven't simplified it yet, but if we were to plug this in a graphing calculator, we would see the graph of what we need to see. However, since this is a sort of an algebraic manipulation class, we will also go ahead and FOIL this out. Now, had these been trinomials like an x squared with 3 terms, it gets kind of complicated to multiply them out, but it can be done. I'll see in the homework if there's anything like that. But we want to use FOIL, so we multiply the first 2 terms, and we get 4x squared. We want to multiply the outer terms, FOIL, right? So that's 4x times negative 5, so that should give us negative 20x. We want to multiply the inner terms, so negative 6 times x gives us negative 6x. And then we want to multiply the last two terms, negative 6 times negative 5 gives us a plus 30. Okay, and so 4x squared minus 26x plus 30. And that would be sort of expanded out. We could graph the same things. They would be the same graph, but just depends on what they're looking for. So far as this feeling like pretty much a review. Okay, good. Question? Of course. Quotient of two functions. This is actually one of the easiest ones. You think, oh, division's hard, right? Well, because division's hard, we get to just sort of leave it as it is. So with this, we've got our two functions. We're asked to divide them. So it's just a matter of rewriting them. And then we're pretty much done. Now, we could potentially simplify if these would factor. So you may get some that are like this, and then the homework may, if you leave it like it is, it might mark it wrong because maybe they factor and they can reduce. And that's why we, in your recitation, in fact, how did those who have the Tuesday recitation, did it go pretty good? Okay. I think she had a worksheet having you do some factoring. Is that, yeah. So that's the kind of thing is, so that's what that class is for. Yes.
What like the practice that we have in recitation is easier than the lesson.
It oftentimes is, because what they're focusing on in the recitation are skills that will help you as we go into the next sort of section. So it might, recitation is not just about working through your homework. Although if they have time, you could, but yes. Right. What we set up is that there will be worksheets for you to work through. We had a discussion again. Jasmine is the one responsible for that grade, but we talked about that basically we just want you there, involved in it, getting as much done as you can, and that those things are going to help you with the homework. But you won't have any additional homework. I'm not having her look at the homework. I'll take care of all of that. So the stuff you do in my math lab, that's set. That's sort of for here. The recitation pretty much is show up and work and do, and learn some things that may be a little different. So there's not but if it's something you haven't seen, it's probably something you will see next week that will help you out. All right. So yeah, maybe this factors. I don't think it does. This would be 2 and 4. Yeah, I don't think it's going to factor any. The bottom's not going to factor. Certainly not going to factor into 9 minus 10x. So we're just done. We're just done. That's the answer. And again, if it was g of x over f of x, it would just be the reciprocal. So that's what we do with these type of functions, and we move forward. So that's combination of functions. Any questions? Any questions? Okay, so that's usually the part that's because you've had experience. It's really just we do it in algebra a lot of times without calling it that. We just say, here, add these two functions. We don't call it combination of functions. But composition is something different. And what happens here is we are putting one function into the other. And what I see is people will almost, because of the parentheses and stuff, people see that as multiplication. So that's the first mistake as I see is you're seeing it as multiplication because there's all these parentheses going on, right? So, and sometimes we call this fog because but it's really F composite G. That little circle is not really an O, but sometimes it's easy to call it fog. F composite G. And again, it's this first notation can be confusing because it's like, well, which comes first? But what it is it's whatever one is closest to the x, that's the one that gets the input first. So x goes into the first function, the closest function, in this case the g function. We get an output, and then we have to put that into the f function. So I wish I had my different colors. I've got to upgrade my license, and I'll have colors by next week, hopefully. So this is sort of like, it's a two-step process. It's first, let's find out what this is, and then when we've got that answer, we plug it in. Good, good. So let's look at an example. And now sometimes we don't get a numerical answer, we just get a function answer. So if we've got these two, oops, I guess I didn't put this. Let's find this composition. So f composite g. So let's look at this. F of g of x. So kind of step by step, that's f. Well, what's g of x? That's the square root of 4 minus x. So that's kind of the first thing to see, is we're taking that, and that gets into the f. Now here's the other part, is what is the f function? Well, it's 3x squared minus 6. But when we go to do this composition, I don't want to write x. I may say x, but I'm going to rewrite x as a big open parentheses, because what's going to happen is my brain over here sees 4 minus x, and then sees another x over here, and I was taught in algebra, x is x, it's the same value, right? But in this case, it really isn't, right? One x is some plastics being made into a steering wheel. The other x is a steering wheel getting put into a car. So they're actually different things. So they're placed for an input. So what I'm going to do is I'm going to rewrite the function as 3x squared, but I change my symbol from x to a big open parentheses, because it's just going to make it easier, and I won't mess up where I put things in. And then I got a minus 6. So you see, this is sort of like a template. I've got it set up, and now what do? Well, what goes in this parentheses? Whatever's in this other parentheses over here. So you see, we did the 2 steps. G of x, I just put it into the parentheses, and now I put it into here. And again, we are sort of done. I mean, we've done the composition. That's the stage. If we graph this, we have the function. However, this is a STEM-based class, so they will want us to do the manipulations to simplify. So we're going to take it to the next step. But I want you to know, as far as composition, we're done. The rest is just algebraic simplification. So then, order of operations, we do the parentheses first, right? If you take a square root and you square it, what happens? They undo each other. Inverse functions, we're going to go there next. So that's exactly what it is. Inverses undo each other. You dig a hole and you fill up the hole. Those are inverses, right? Square root, square it, those are inverses. So this just simply becomes 3. I'm going to leave this here because I apply this, get rid of the square root. It's 4 minus x minus 6. And I did that because if I took the parentheses off too early, I might not know, does that 3 also apply to the 4? Or does it just apply to the x? Or does, and with those parentheses, I see that 3 has to distribute through. So I'm doing order of operations. I did the parentheses, did the exponent part first, got rid of the square, and then now I do the multiplication part where I distribute this 3 to both of these terms, right? So 3 times 4 is 12, minus 3x minus 6. And then now I can take 12 minus 6, gives me positive 6 minus 3x, and that's as simplified as I can get it. Okay. How's that? Feel comfortable? Okay. So just the key part I'll say is whenever you're working with functions and you're going to plug things in, is rewrite the template, change x to a big open parentheses. That's where you can put things, and you'll have maybe no problems. Once I started doing that, I had no problems. Before I did that, I had lots of problems because I'd put things in the wrong place, or but it makes it clear. Inputs go into parentheses. So, and again, sometimes it seems like, oh, do I have to do this? It seems like extra writing. Maybe sometimes you don't, but if you do it all the time, get in that habit. you'll find that you'll make fewer errors. Okay, so now the other part we do with this, because we're building you towards calculus, it's not so much important that you can make a composition, but it's important sometimes in calculus that you see a function as being a composition that was already done. And you need the pieces, because the pieces will be easier to work with in calculus than the big function. So going backwards is always a harder thing to do, at least for me. I don't know, some people are really good at going backwards. Me, I'm good at thinking kind of in one direction, and going backwards is you lose some of the stuff. So what we're saying is now and sometimes when you go backwards, especially with these, there's more than one right answer. There's more than one way to do it to get to that result. So this is one is breaking it into a composition. So we start off with this function 4x squared minus 5. And neither one can be the identity function. The identity function is just f of x equals x. And that makes it too easy. If you make one the identity function, it's one's x and the other is, it's just like it is, right? So how could we break this into two pieces? How could we break it into f of x function and, well, how can we get this to be f of g of x? So what function could we take g of x to be that we plug it in? And even looking at this, how do I, it's kind of a problem solving thing, right? Because there's multiple things. And I have to kind of think of, if I've done enough problems where I've done composition, I'm trying to think backwards.
X to the power 6 minus 5 as g of x.
X to the power of 6 minus 5.
Yes, as g of x, and take 4x as f of x.
Okay. So let's see what happens if we take this composition. So this is always, we take a good guess, and then we actually do the composition to see if it's going to work for us. So I want to take f of g of x, so that would be f of x to the 6 minus 5, right? What is my f function? Well, that's 4 times parentheses. When I fill that in, I'm going to get x to the 6 minus 5. It's looking good.
I missed 5 by 4.
Okay, good. But see, this is cool. This worked. But then as we do this, what are we going to get? We distribute the 4. We get 4x to the 6, which is good. But then we get 20. Oh, I don't want 20. Oh, what if I do this? Now, okay, so this was a good try, but this needs to be divided by 4. Now I've got two functions that will do this. Do you see how that? But that's not the only, I mean, probably we could come up with something else. But that's the thing is try to break it into two pieces that are something different. As you do the composition, you'll see whether it works or it doesn't. And oftentimes, if it doesn't work, you'll also see what little adjustment you need to make. The problem is in math is we're always trying to get it right the first time, and we put ourselves through too much stress. It's usually best to make a mistake the first time and fix the mistake. That's a lot of times less stressful. And I know engineers, it's like, well, I can't make any mistakes. No, we got to make mistakes. We got to feel free to make the mistakes. Do it in a safe environment and realize that those mistakes are going to help us find the right answer. And after, I said, the more mistakes you make, the more you learn. I think it was Andrew Carnegie, some rich guy. He said he would rather have he would like to have an employee who's made mistakes before and recovered from them, because he knows that people are going to make mistakes, but that it's not the perfect person you want. It's the one who knows how to recover from mistakes. So yeah, so this got us there. Okay, we didn't want 20, so the way we could do that divided by 4, and we're good. Yes.
The input is G or F because I don't understand.
Oh, sorry. Yeah, so over here, the input is, because G is closest to this, G is going to be the input into F.
And about H.
And H is the end result. H is the final function. So this is H up here. So it's like, what are the two pieces that we combined, we put in a composition to make H? And they gave us the definition here. They want F of G, so they want G to be what gets put into F. The other thing I see with this is people will come up with the two right functions, but they might put them backwards. So that's why you always want to test it out, make sure you're going in the right direction, because it's different, right? If we did G of F of X with these two, it's not going to work, right? Its order is important here. Another thing we could do, and this is sort of what might be simpler, is let's give this a try. What if I had G of X be equal to X to the sixth, which is okay, that's not the identity function. What would F of X need to be? Well, it needs to be a function that when I plug X to the sixth into it, I end up with 4X to the 6 plus 5. So the other way I could do this is 4x minus 5. So it looks very similar, but remember those x's are really, when I'm doing composition, they're different things. They're really, x is just, actually I was back at Oregon State, a student made the mention that x just marks a spot, like on a treasure map. In functions, x is just marking a spot where the input goes. In composition, when I see this, right, f of g of x, let's do this. So I'm going to put f of x to the sixth. And what is f? It's 4 parentheses minus 5. I put this x to the sixth in here, and that works. So here's a solution that works. I could do a composition of these two functions, and here's a different function setup. It works as well. And I thank you for putting that. Sometimes I see one way, I don't see that there's a second way, but typically there are. So it's good when you suggest things for us, we can see multiple ways to do things. Okay, you just go with what you can see. Questions on that part of the, okay. And again, it's just not, I tried to let you know why we're doing this, and it is because when we get to calculus, if we have these two separate functions, it may be easier to actually find the derivative. And actually, we use something called a chain rule, where knowing the pieces makes it easier to work with. Now, the function h of x to get its derivative is actually not too bad either, but there's some cases where we might want to break it into two functions. Okay. And this is one of my favorite questions, because they threw this at me when I was doing my interview, and I kind of froze up on it. They still hired me here, so that's good. But it was one of those things that was kind of at the end of the day. And so I always remember this question. If we have the composition of two functions, what is the domain? Okay, because remember, we're going to put the domain is what x's can we use as inputs. Those particular domain, those particular exercises only go into one of the functions, and then something's happening to it, and then that goes into the other function. So there's two places we have to check for domain when we're doing a composition. We always have to check the first input is, if we put in a value for that first value, will we get a real number output, or will we get division by 0 or something? So we're doing f composite g. So I'm going to rewrite this as that the g gets plugged in first, right? Or that x gets plugged into the g function first. So there's our g function. This is the first place we have to check. What values of x can I not use in this function here, 11 over x? 0. And 0 is the only one, because division by 0 is undefined. So rational functions, that's really all we're concerned with, is what would cause division by 0. So what I notice right now is I'm going to say, okay, my domain I'll just do it like up here. This is my notes. X can't equal 0. That's a given because that's the input. If I put in 0 right now, boom, I'm done. Because once it's undefined, you can't work with undefined, right? What do you do with undefined? I don't know. It's undefined, right? So we're undefined. But what we have to do is we have to go to the next step. We also have to see there might be a value that we put in there that causes problems down the road. So then we go down the road. What we're going to see is we never really look at just the f function by itself because we don't need to. Because 0, if x was 0, it does not get plugged into the f function, right? Actually, it doesn't, causes a problem. So then I go ahead and do the composition. Well, what's the composition? It's 4x minus 3, right? So I always write it this way. Just put a big open parentheses. What goes in that parentheses? 11 over x. Okay. Because then again, this is a place where if I don't put those parentheses, I have a mental breakdown, sort of, how do I put 11 over x in for x? That doesn't, I feel like I'm breaking a rule, and I probably am. But if I just say, well, x is marking a spot, these x's are different, I don't have to explain all of that if I just do the parentheses. Okay. Now, what would cause us a problem? Well, we can kind of see we would get division by 0 if 11 over x were equal to 3, right? Because 3 minus 3, that's going to be a problem. But they probably also want us, in these questions, they will ask us to actually do the composition. And then they ask us about the domain later. So let's go ahead and simplify this. Because that's one of the questions we're going to ask. So how would I simplify this? I've got basically a complex fraction, because it's really not pretty to have a fraction within a fraction, right? At least I never thought it was pretty. Sometimes it's cool, but how could I get rid of that fraction in the denominator?
You can take the LCM of the denominator.
Good. So the denominator, one way is, and again, the book I had, it called this killing fractions, or maybe it was my students who called it killing fractions. If we multiply by the denominator, it will cancel out the it'll cancel it out, right? So if I multiply the bottom by x, it's going to get rid of it there. But can I just, let's just multiply the bottom by x. Is that, no, I just can't do that. But what could I do? If I multiply the bottom by x, and the numerator by x, what am I really multiplying by? 1. I can do that all day long because 1 doesn't change anything. Okay, 1 doesn't change anything. So the trick here is to multiply both the top and the bottom by the LCM or the denominator. The key part is in the bottom, you're going to remember you're going to need to distribute this x to both terms. The top, it goes up here, so I end up with 4x. X here, 11 times x, 11 over x times x, the x's cancel, so that gives me 11, and then I get negative 3x. So I have simplified this into no longer being a complex fraction, and that's what the answer I would put in as the composition of the function. That's what they're going to look for. When I think of domain, though, what do I need to be concerned about? The denominator being 0. I don't really, it's okay for the numerator to be 0, but the denominator cannot be 0. So I look for where it is equal to 0, and then I'll take it out. Okay, so you could either subtract 11 from both sides. Why not? That's how we would usually do it. Negative 3x equals negative 11, and then divide by negative 3. So you get that if x were ever equal to 11/3, we would have problems. So we're going to say up here on the domain also x cannot equal 11/3. So we kind of do the analysis with x equal to 0, or the thing equal to 0, but that's telling us what it can't be, right? That's telling us what we have to take out. And then we put those two pieces that they can't be either one of those. It can't be 0 because it would cause us problems at the beginning. And it can't be 11/3 because that would cause us problems when we down the road. It would be okay initially. It would be okay initially. We'd have a value, but that value would cause us problems in the composition. Okay. And the way we list this, I always like to draw the number line. Let's see, 0 is here. We can't have that, so I'm going to take that out. And then 11/3 is like somewhere over here. What's that? That's like 3 2/3 or something. So I need to take that out. There's negative infinity here. There's positive infinity here. Those are the 2 points I'm taking out. So everything in between is okay. So with interval notation, I write this as going from negative infinity, parentheses, all the way to 0, parentheses. And then I've got this middle section, so I put a union. Then I can go from 0 to 11/3, parentheses, union, 11/3 to infinity. Very complicated way to write. I can't be 0 and I can't be 11/3. But this is where our world has gone. We go to interval notation. Back in my day, we could just write this up here. We say it could be anything except these two, and we're good. But they changed, so we do what we need to. So that's interval notation. They would want this question answered this way. Question? Yes?
I have a question about the domain. Would those be considered the zeros of the function?
No. Those the zeros of the function are where the numerator would be 0. So yeah, so good. It's always confused. What's 0? Well, when we talk about the zeros, that's where it crosses the x-axis. So y is 0, but x is something else. These would be the places where the function would become undefined. We'll see a little bit later. They're also there's the asymptotes. Yeah, when we get to rational functions, we give them a name. They're really the asymptotes. And they're sort of a place where there's a hole in the graph because you can't really plug it in because it shoots off to infinity and that kind of stuff. How are we doing so far? Making sense? All right. I think we're almost done. Yeah, we're done. Okay. So then, again, this is set up for my other course, but you've got the ideas. Now you're ready to really take a look at the 1.7 homework. And again, we can have, after class, I've got office hours. If you have questions on the homework, we can take a look at those. Also, I think what I'll post that maybe like Friday afternoons. I have no classes on Fridays, but that's a good time if you want to get online and do some virtual office hours, so through Zoom. And what I'll do is if someone signs up for one, like I've got a 2 o'clock appointment, but it's for my 210 class. If someone from here signs, I will put out an announcement, hey, I'm having a meeting at 3 o'clock or whatever. If anyone else wants to join, go ahead. It's okay. Because maybe you just want to, I've had some students who I just want to sit and watch other people ask questions because I know it'll help me. I don't know what questions I have yet. That's fine. So I'll kind of, we'll have sort of fluid office hours. If you need them, request them. We'll put them there, and then I'll let everyone else know. But it's really hard for me to just, I could set 3 o'clock to be a standard office hours, but it might not fit with anybody's schedule, so it's like nobody ever comes. But if 4 o'clock works, so I'll let you guys see if you need it, set it. There's also the resources of, actually, let me stop this.